So this video is for E5 Fusion and Stars, the paper 1A questions. There were only a handful of HL questions, so I threw in SL and HL, and it still only gave me 10 questions. I think it's based on what's available in the specimen tests and the examples and all of that. Anyway, so sequence of the evolution of a main sequence star of about 2 solar masses, which is about the same as our sun. So our first question here talks about a main sequence star of about 2 solar masses and said what's going to be the evolution of a main sequence star of about 2 solar masses, which is very close to our own sun. So we're not talking about a red supergiant here. Something that's kind of like our sun. Our sun will eventually become a red giant, but it's not going super giant, so it's not getting that big. And then it's like, okay, fine. We have 2 choices that are red giant. It's like, well, what happens after a red giant? Well, red giant tends not to go supernova, but if a star does go supernova, the whole thing explodes, right? Supernova, right? So then supernova does not go to white dwarf. There's nothing left after the supernova, so it can't be this guy. This is the evolution, red giant, planetary nebula, white dwarf. I can illustrate how that works. Red giant star. Eventually that red star gets bigger and its outer layers start to kind of move away from it. It starts to get a little less spherical. But then in the center you have the core of the star, which is white hot. Eventually these outer layers of the planetary nebula really start to drift away from the star altogether. Maybe that material might become planets in like the next evolution, but it drifts away from the star, and what's left, it's supposed to represent space. What's left is that core, which becomes a white dwarf, and it's a dwarf because it's just the core of the star that was there before. But anyway, so that is number 1. So number 2 uses the luminosity equation from B1. But it is related to stars. And so we have luminosity is Stefan-Boltzmann constant times the area times the 4th power of temperature. And the chart has luminosity versus temperature. Now, it's asking about the ratio of radii, so we have to use the area and put pi r squared in for radius. If we solve for radius, we get radical L over Stefan-Boltzmann constant times pi times the 4th power of temperature. We can see from the chart that the y temperature is 1 quarter the temperature of x, because HR diagram's temperature goes down to the right, which is weird, but that's the way it rolls. And so the ratio of x to y in terms of radii is radical L over Stefan-Boltzmann times pi times the 4th power of x temperature divided by the same fraction on the bottom for y. And so we can actually, if you are dividing radicals, it's the same as multiplying times the reciprocal, same thing for fractions. And so all of the constants, you can cancel them out. And we know that y has 1 quarter the temperature that x does. So, and after all that, the ratio is 1 over 16, which is choice A, and it agrees with the mark scheme. A lot going on there. Number 3. So for number 3, it says, which process is the primary energy source in a red giant star? And so we're talking about stars, and the energy source in stars is fusion, so not gravitational contraction. So we have fusion of hydrogen in the core, fusion of helium in the core, or fusion of helium in the shell surrounding the core. And I think it's important to note we're talking about a red giant star, which is usually towards the end of the star's life. And usually the way stars work is we're talking about hydrogen fusing into helium, but we're talking about a star towards the end of its life. So we're not talking about the fusion of hydrogen here, we're talking about the fusion of helium. And that fusion doesn't happen in the shell, it happens in the core. And so 3 is C. And so 4 has 3 different stars, P, Q, and R, and they're plotted on this HR diagram by the circles. And it asks, which is the order of the stars in the order of increasing radius? Well, luminosity is Stefan-Boltzmann constant times the area times the 4th power of the temperature. area is pi r squared. So if we solve for the radius, we get that it's square root of the luminosity over the Stefan-Boltzmann constant times pi times the fourth power of the temperature. Now P and Q have the same luminosity, but the temperature of Q is greater than the temperature of P. P and R have the same temperature, but the luminosity of P is greater than the luminosity of R. Okay, let's fix that, because I forget with the HR diagram is that the y-axis increases vertically, but the temperature axis increases to the left, which means that the temperature of P is greater than the temperature of Q. And temperature is raised to the fourth power, so temperature is going to have a greater influence than luminosity will. So as temperature goes up, radius goes down, and so in order of increasing radius, P has a smaller radius than Q does, and then because P has the higher temperature, and again, R is inversely proportional to square root of 1 over t to the fourth. So temperature has the greater influence. So P is tight and Q is big, and then comparing P and R is directly proportional to the square root of the luminosity. So as luminosity goes up, then the radius goes up. And P has more luminosity than R does. And so R is going to be in the middle. So in terms of increasing radius, we have P, then R, then Q. Wait, no. This is so annoying. Sorry, yes. P has a greater radius than R does. So in order of increasing radius, since P has a greater radius than R does, R is the smallest. Then P comes bigger than that. Then Q is bigger than that. So it's RPQ, which is D. Choice D. Again, I feel like I confused myself, so let me go over that one more time. So looking at P and Q, right, P and Q, then they have the same luminosity, but they vary by temperature. And P has a higher temperature than Q does because temperature increases to the left. Radius is directly proportional to the square root of 1 over t to the fourth. So P, with a much higher temperature than Q, is going to have a much tighter radius. Therefore, Q will have a bigger radius, will be a bigger star than P. So if we're going in increasing radius, Q is on the right. Q is the biggest star, or bigger than P at least. All right, now let's compare P and R. P and R have the same temperature, but different luminosity. So now I'm looking at how radius is directly proportional to the square root of L. P, with a greater luminosity than R, is therefore going to have a greater radius, so P is going to be larger than R. So R is going to be the smallest, P is going to be bigger than R, and then Q is much bigger than the two of them because T is raised to the fourth power. So in order of increasing size, we have R, P, Q. There. All right, choice D. Number 5 will wind up using the same formula. It says star X has the same temperature of the sun and a luminosity of 10 to the fourth, the luminosity of the sun, and then it's comparing. Question says, what is the radius of X over the radius of the sun? I hate how they break these questions. So it says X has the same temperature, but 10 to the 4 luminosity. So we're comparing radii, where X has the same temperature as the sun, but 10 to the fourth luminosity. All right, well, the formula for radius, we have it right over here, is radical L over Stefan-Boltzmann times pi times t to the fourth. Square root all that. Did I say that? Square root all that. And so we're looking at the ratio of radii. Well, the temperature is the same, so that fourth power of the fourth power of the temperature does not matter. But X has 10 to the 4 the luminosity that the sun does. So looking at the ratio of the two, we basically are left with radical 10 to the 4. Because the constants are all the same, the temperature is the same, just the luminosity is different. And so square root of 10 to the 4 is 10 to the 4 to the 1/2, which is 10 squared, which is choice B. All right, that's about 10 minutes. We're about halfway through. I think we can knock this out in about 15 to 20 minutes if I'm efficient. But I will come back to this later. Okay, so for number 6, it says star is on the main sequence star. And it says the abundant elements in the core and in the outer layer. Well, for a star on the main sequence, in the core, we're going to be having hydrogen fusion. And then the hydrogen is being fused into helium. And then the helium winds up in the outer layer as the remaining hydrogen that's in the core continues to get fused under the normal lifetime of a star. Once that fusion starts to run out, then the nuclear pressures become less. Not the nuclear pressure. The mass itself of the star becomes less because as hydrogen fuses into helium, there's some of that mass defect that turns into energy by E equals mc squared. So the star is actually losing mass, and by losing mass, it's losing gravitational attraction in towards itself, being able to hold itself together. So it actually increases in size because with less mass to pull inward gravitationally, it starts to expand outward. But it's like, well, as it's losing mass, where is that mass going? The mass of hydrogen, some of that hydrogen is being lost as it fuses into helium. But during the normal lifetime of a star, there's the hydrogen furnaces fusing away in the core and then pushing the helium out to the outer layer. So that's B. Number 7, we are comparing a star and the sun. The things that we're comparing are radius and luminosity and temperature. So let's go back to that equation for the formula for luminosity versus temperature. All right, and so temperature is the fourth root of luminosity over Stefan-Boltzmann constant times pi times r squared. And so this new star says it has 13 times the radius and 400,000 times the luminosity. Do you like how they broke that 400,000 across lines? They're killing me here. All right, so we're going to get a proportional change, and then we can apply that proportional change to the original surface temperature of the sun. So 13 times the radius, 400,000 times the luminosity. Get rid of the Stefan-Boltzmann constant and pi because those are constants. All right, let's see what the proportional change is. Okay, so when you run the numbers through, you get that the temperature of the new star is roughly 7 times the temperature of the sun. And so 7 times 5,700 is 39,900, and so if we round that off to 2 sig figs, we get 4 times 10 to 4.0 times 10 to the 4, which is A. We're using that formula a lot. Likely outcome for a star with the same mass of our sun. So our sun is on the main sequence, and so we all start with the main sequence, fine. Now, based on the mass of our sun, it's not going to become a supergiant. It's not massive enough. So we're not going main sequence supergiant. We're going main sequence giant. Didn't we see this question already? We saw a very similar question. So yeah, this guy's very similar to number 1. But anyway, it goes main sequence, red giant, not supernova. It's not going to completely explode. It's not big enough. It's going main sequence, red giant. Those outer layers are going to drift away into a planetary nebula, leaving behind the core, which is a white dwarf. So 8 is B. And the mark scheme over here says, yes, indeed, it's B. Okay, 2 more. Number 9. Okay, so for number 9, we have deuterium and tritium giving 0.019 universal mass units worth of energy in fusion. And also they make reference to uranium-235 in fission, giving 0.190 universal mass units. And I say, what's the ratio of the specific energies? So specific energy is the ratio of the amount of energy to the mass itself. So when I say 0.019 U over 5U, the 5U I'm getting from the nucleons of the 2 hydrogens. So that's 2 plus 3, 2 for the deuterium, 3 for the tritium. And then for the uranium-235, that's 235. So it's kind of like a ratio. And so that in and of itself, the specific energy is a ratio, and then it makes reference to the ratio of the specific energies themselves. So that's why I have 0.019U over 5U over 0.190U over 235U. So when you do that compound fraction, you wind up with 4.7. 4.7, when you round it off, becomes 5. And so our ratio is 5, which agrees with the mark scheme. And now we have number 10. We have carbon and hydrogen undergo nuclear fusion to form nitrogen and a photon. What is the number of neutrons and nucleons in the nitrogen nuclide? And so this is a pretty basic question. It's because the photon has no charge, there's no nucleon count for the photon. So in terms of nucleons, we have 12 for carbon and 1 for hydrogen, giving 13 for nitrogen. And in terms of protons, we have 6 and 1, making 7, which is what makes it nitrogen. And so the number of nucleons is 13, and the number of neutrons is 7. Wait, no, no. Right, the number of protons is 7. Protons is 7. And so the nucleons is 13 minus 7 for the protons gives 6 neutrons. Read carefully. I almost said 7. And so we have 6 neutrons and 13 nucleons. That's dirty, because 713 is choice A, right? It is not. It is 613, choice B. Okay, and that is it for the A1 questions for E5. We'll see what the paper, no, A1, 1A questions, and then we'll see what the paper 2 guys look like. Thank you.